Hello and welcome to Empowered Learning. This is part 3 of the videos that pertain to calculating the volume of a solid where we have solids of revolution while we're taking an area and rotating it about some vertical or horizontal axis. And so in this last set of examples here, we have the two functions y is equal to negative x squared and y equals negative 1. And what we want to do is find the volume of the solid that is generated by the area that's bounded in between those two functions that were aforementioned, and rotate them about several different axes. And so the first one that we want to do is we want to rotate this bounded area about the line y equals negative 1. So first thing that we see here is that if we draw y is equal to negative x squared, it looks like this downward opening parabola. And of course, y equals negative 1 is this horizontal line. And the area that's bounded by it is in here. So what we need to do is find out where these two curves intersect, because that is going to be where our limits of integration will be. So we'll go ahead and handle that first. So we're looking here and we know that negative x squared and negative 1 need to equal each other. So if we multiply both sides by a negative 1, that becomes positive x squared, positive 1. X squared equals 1. And so x is just equal to plus or minus square root of 1, which is just plus or minus 1. So here we know that this will be negative 1. Here we know that this will be 1. So those will be our limits of integration. So the next thing that we note here is that since the axis of rotation is the line y equals negative 1, and the area that's bounded in between the two curves has no gap in between it, this is why we're using the disk method. And since we're using the disk method, we know that our area is going to be defined as pi times the radius in terms of x quantity squared. And we know that we're going to be defining the area in terms of x and thus integrating in terms of x, because we are rotating this area about a horizontal line. So horizontal line, rotating about a horizontal line means that we integrate with respect to x and define our functions with respect to x. If we rotate about a vertical line, then we integrate with respect to y and define our functions with respect to y. So for us to be able to figure out what this radius is in terms of x, note that the radius here, and I'll erase this, is actually the difference in between these two curves here, or I'll put it here, these two curves. So I'm going to define it that way. So we know that this first curve here is a negative x squared, and we take the difference in between that and the curve y equals negative 1, so we just put negative 1 there. And of course, subtracting negative is the same as addition, so we see that our radius here in terms of x is just 1 minus x squared. And so now that we have a way to define what the radius is in terms of x, of course, if we square that, then of course that's just 1 minus x squared squared, which is just 1 minus 2 times x squared plus x to the fourth when we FOIL that out. And so now that we have a way to express the radius squared here, we know that our formula for volume is just going to be the integral from negative 1 to 1 of pi times r of x quantity squared dx. And one thing that we note here is that this area on the left half is equal to the area on the right half. So we could rewrite this as 2 times the area from 0 to 1 of pi radius in terms of x squared dx. And of course, looking at it that way, that's just 2 pi integral from 0 to 1. And of course, in place of r of x quantity squared, we would write 1 minus 2x squared plus x to the fourth dx. And so from here, we'll just integrate this function by taking the antiderivative of each term and then evaluating from 0 to 1. Okay, so from here, if we take the antiderivative of 1, it's just x. Antiderivative of 2x squared is going to be 2x cubed divided by 3. And antiderivative of x to the fourth is x to the fifth divided by 5. And all that gets evaluated from 0 to 1. So from there, of course, we plug in 1 for everything first. So it'll be 1 minus 2/3, 1 cubed, plus 1/5, 1 raised to the 5. And let's get that looking a little nicer. And then minus for 0, if we plug in 0 here, here, and here, all of that will be 0. So we don't waste our time writing that. And then this is 2 pi. 1 minus 1 cubed is 1. 1 times 2/3 is 2/3. Plus 1 to the fifth. 1 raised to the 5 is just 1. And that's just 1/5. And from there, we know that 1 minus 2/3 is just 1/3. And 1/3 plus 1/5, we could kind of do 1 times 5 is 5, plus 1 times 3 is 3. So it'd be 5 plus 3, all that divided by 3 times 5 is 15. So then from there, we have 2 pi, and this is 8 over 15. So our final result here ends up being 16 pi over 15. And of course, this will be in cubic units. And let's try to write that a little better here. So in cubic units. So that's how we handle this first example. So the next example that we do, we'll see that we're going to have the same area, but now we're going to rotate the area about a line where there's going to create a gap in between the area and the axis of rotation. And so because of that, we're going to have to use the washer method for this next example. So you can see that for this next example here, same exact area bounded by the two curves y equals negative x squared and y equals 1. But now we see that now we're rotating about the line y equals negative 2, which is 1 off from, well, negative 1 off from where we were. Let's go ahead and note here that this is still negative 1 and this is still 1. So the only thing that's different now is that we now have to properly define what the outer and the inner radius is. Okay, so if we look at the outer radius, then of course the outer radius, again, we could define this as the difference in between the curve negative x squared and the curve here y equals negative 2. So if we did that, that would just be 2 minus x squared. The inner radius can be defined as the difference in between the curve y equals negative 1 and y equals -2, which is just -1 plus 2, which is 1. So, of course, you could also just interpret that the inner radius here, the distance from y equals -1 to y equals -2 is just 1. And the distance from for the outer radius would just be 1, well, actually 2, and then you just take away the x squared part for wherever you're at. So you could kind of look at it that way too. Just depends upon how you see and process things. I know for me better, it just makes it easier if I just look at the actual functions that's defined and just take the difference out. But it's up to you. So now that we have this, since we're using the washer method, we know that the area in terms of x here is going to be defined as pi times the outer radius squared minus the inner radius squared. And so that means here we need to find out what the outer and inner radii are squared. And so this would be 2 minus x squared squared. And this will end up being 2 squared is 4. And then 2 times -x squared times 2. So that would be a minus 4x squared. And then negative x squared squared is a positive x to the 4th. So that's what the outer radius squared is. The inner radius squared will be just 1. And so thus, we know the area in terms of x here is just pi times outer radius squared minus inner radius squared, which would just be pi 4 minus 4x squared plus x to the 4th minus 1, which will just end up being pi times 3 minus 4x squared plus x raised to the 4th. So now all we have to do is integrate that now. So therefore, now our volume is going to be defined as integral from -1 to 1 of pi times 3 minus 4x squared plus x to the 4th dx. And again, since these areas here, if we scroll back up, since the area on the right side here is going to be equal to the area on the left side, we can rewrite this as 2 times the integral from 0 to 1. So we'll go ahead and do that. It's equal to 2 times integral from 0 to 1. And we'll go ahead and put the pi out there too. And that will just be 3 minus 4x squared plus x to the 4th dx. Make that look a little better. And now all we need to do is just integrate. So we got 2 pi, and antiderivative of 3 is 3x. Antiderivative of x squared is just x cubed divided by 3. So this would be 4x cubed divided by 3 plus antiderivative of x to the 4th is just x to the 5th divided by 5, or 1/5 times x to the 5th. And that gets evaluated from 0 to 1. Plug in 1, first set of terms. And then we plug in 0 into those same set of terms, and this gets 0. So from there, we have 2 pi, and we just end up having 3 minus 4/3 plus 1/5. And then we just simplify from there. So we know that 3 is the same thing as 9 over 3 minus 4 over 3 plus 1/5. That's 2 pi. Now we have 5 over 3 plus 1/5. And of course, from here, we can do what we have been doing in the previous examples, 5 times 5 plus 3 times 1, which will give us 28, all over 3 times 5, which is 15. Come here, that's 25 plus 3 over 15, 28 over 15, and that ends up being 56 pi over 15, and that is in cubic units again. And so our last example will be somewhat similar to this one, but instead of the axis of rotation being under the bounded area, it's going to be above the bounded area. So the way that we'll define the outer and inner radius here, it'll look different, but if we use the convention of just taking the difference in between the function that's furthest from the axis of rotation minus the axis of rotation, then it should be pretty easy for us to define. So for our last example again, you see we have our drawing here of y equals negative x squared here, and y equals -1. Just as we said before, we know that limits of integration here are from -1 to 1. And so now the thing that's different is we need to define the outer and inner radius again, where the line is at y equals 1. So we're rotating about this line now. So if we use the convention of saying the radius is going to be the function furthest from the axis of rotation minus the axis of rotation, we should get exactly what we need every time without having to do a whole lot of thinking. So if we look here, the outer radius, the functions furthest away is going to be -1. And then we're going to take -1 and the difference in between -1 and the axis of rotation, which is 1. So that ends up just being -2 here. And of course that makes sense because the distance from y equals 1 to y equals -1 is a distance of, it's a distance of 2, but in relation to y equals 1, it's 2 in the negative direction, okay? Now for the r sub I, of course, that's the difference in between negative x squared and the axis of rotation, which is just y equals 1. So in this particular case, we end up getting a negative x squared minus 1, okay? And so again, if you wanted to, you could find a way to redo this another way. So let's say if you want to define this in terms of just distance, so the distance in between y equals 1 and y equals -1 is just 2, and the distance here is going to be from y equals 1 to the x-axis is 0, and then from 0 downward to this parabola is a distance of x squared again. So you could define it as 1 plus x squared. And you'll still get the same answer either way. Of course, This is just doing it in terms of what the actual functions are, and this is just doing it in terms of distance. Both ways will get you the same answer. Okay. To keep with the convention that I've been doing in the previous examples, I'm just going to keep this way that I've been doing it up here, the very first way that we did it, and we'll just carry on doing it that way. All right, so now we have the outer radius and the inner radius. So the outer radius squared, of course, is just 4. And the inner radius squared, it's just this squared, which I will factor out the negative here. So that will be a -1 squared times this squared, x squared plus 1 quantity squared, which of course we know this is just a +1. So we just got x to the 4th plus 2 times x squared plus 1 whenever we FOIL out x squared plus 1 quantity squared. Okay, and let's fix that 1 here. All right, so now that we have that, we know the difference in between these is just going to be 4 minus x to the 4th plus 2x squared plus 1, which when we distribute to all three terms here, 4 minus x squared minus 2x squared minus 1, which just ends up being 3 minus x to the 4th minus 2x squared. And so this is what we'll use. Our volume, again, is from -1 to 1 of the area, which in this case is pi times the outer radius squared minus the inner radius squared, which would just be all this business here. The 3 minus x raised to the 4 minus 2x squared dx. And of course, since we know the areas again on the left side and the right side are equal, we could really just rewrite this and say 2 times integral from 0 to 1. We'll put the pi out here, and this will be from the integrand will be 3 minus x squared, 3 minus x to the 4th minus 2x squared dx. And so from this point, we'll just do antiderivative like how we've been doing and figure out what the answer is. All right, so equal here, and this is 2 pi. And when we evaluate everything at 1, of course, first thing we need to do is just take the antiderivative of each term. So the antiderivative of 3 is 3x. Antiderivative of x to the 4th is 1/5 x to the 5th. And antiderivative of 2x squared is just 2/3 x cubed. Evaluate that from 0 to 1. And of course, plug in 1 for x. And minus, plug in 0 for x, and everything goes to 0 there. Make this let's get that 5 looking right here. Okay. And so now we have 2 pi, 3 minus 1/5 minus 2/3. And of course, 3 is the same as 15 over 5. So we'll say that's 15 over 5. So that gives us 15 minus 1, which is 14 over 5, minus 2/3. And then 14 times 3 is 42, minus 5 times 2, which is 10, all that over 15. And so we got 2 pi times 32 over 15, and that ends up being 64 pi over 15, and that is in cubic units. So we see, based upon where the axis of rotation is placed, that's going to let us know whether we're going to use the disk method or washer method. And of course, in the cases where the area and the axis of rotation doesn't have a gap in it, we know that we're going to use the disk method, whereas if it does have a gap in it, we use the washer method. And then of course, if we're stacking areas to form a shape, then that goes back to this solids of non-revolution. Okay, and so this concludes my examples on calculating volumes of a solid where we're actually doing solids of revolution. I hope all of these examples help. Let me know if you like it or not, and thank you for checking out the video. Tune in to the others I'll be recording soon.